So in this video, what I want to do is to use calculus to model free falling but with air resistance. And on this slide, what I'm going to do to get our convention straight is talk about something falling but without air resistance, so just free fall. And so in that situation, we have the force of gravity, and if we're near the Earth, we can just say that it's the mass of the object times g, where g is the acceleration due to gravity, and it's approximately constant. And from Newton's second law, we have that F is ma, where a is the acceleration. So if we neglect air resistance, this is the only force, and we have ma is equal to mg. The masses cancel, and a, the acceleration, is little g, the acceleration due to gravity. And just to be clear about this, we can write acceleration as the derivative of velocity with respect to time. And because velocity is the derivative of position with respect to time, this is also the second derivative of position with respect to time. Now, when we're discussing such situations, we are using vectors, and in one dimension, if we're just thinking about something falling down, there is a minus sign convention for your vectors. And the one that I'm going to use in this video is I'm going to say that x increases downwards. So I'm measuring, let's say we're here, x is 0, and as it drops, x becomes larger and larger. And that corresponds to a sign convention. I could alternatively have said that this is x is naught, x increases that way, and x is becoming negative as it drops. So there is a sign convention. This is the one that I am going to be using. So this sign convention is built into this, because otherwise I would have a minus sign. I would not have that d2x dt squared is plus g. I would have d2x dt squared is minus g were I to use this convention. So let's now just solve this situation. And what we have is that dv dt is g. That's just writing this out with a being the derivative of velocity with respect to time. So we can integrate that, and we get that v is gt plus a constant. And now we say, well, if at t is naught, v is 0, then our constant here is equal to 0. So we have that v is g times t. And we can integrate that again. And if we integrate again, what we obtain is that x, which is the integral of v with respect to time, is going to be 1/2 g t squared plus some other constant, which I'll just call c again. And if we say that at t is naught, x is naught, then again c is 0. So this is the standard way of solving such problems when we don't have air resistance. And this equation here, that x is 1/2 gt squared, that is related to the very familiar situation when we have constant acceleration, as we do here, because a is just g, and we're treating g as being approximately constant. So we have the constant acceleration equation that s is ut plus 1/2 at squared, where a is equal to g, and we've said that u, the initial velocity, was 0. So that's just a special case of that. Okay, having gone through the basic ideas, on the next slide I'm going to add air resistance. So on this slide, what I want to do is to set up our model of including air resistance in our modelling of an object that is falling. So on the previous slide, we had the gravitational force, which acts downwards, and our object is accelerated by it. And as the object starts to move, there will be an air resistance opposing that, and as the object falls faster and faster, the air resistance will increase. And the model that I'm going to use in this video is that the size of the air resistance force is proportional to the square of the speed of the object that is falling, and it is opposed to the direction of motion. So because I am considering an object which is falling downwards, air resistance is going to be acting upwards like this, and I put in a minus sign to show that it is acting upwards. And C is a constant which will depend on the object itself. For example, if you flatten out the object and have a larger area, then C would be larger, but I'm just going to treat it as a constant and not worry about the details of it. So the net force acting downwards is F is ma, so that is the mass times the derivative of the velocity with respect to time, and that is equal to the gravitational force and the air resistance force, which is opposed to it, hence this minus sign. So we have that the mass times the derivative of the velocity with respect to time is mg minus c, our constant, times v squared. And now we want to solve this equation. And what I'm going to do on the rest of this slide is just to rewrite this equation in a nice way and introduce the concept of the terminal speed. So let me start off by dividing both sides of this equation by the mass. So if we do that, what we obtain is that the derivative of v with respect to time, v dot, is equal to g minus c over m times v squared. Now let's just think about what happens when we let go of an object from rest, which is the situation I'm going to consider here. Initially, v is 0, so the acceleration is just g, and the object starts to fall and it starts to accelerate, so v becomes larger. As v becomes larger, the net acceleration is going to decrease. So instead of it's going to be g, it is g minus this ratio of constants times v squared. And what you can see is that if you let it fall from a great enough height so that v can become large enough, then at some stage this term will be equal to that and the acceleration will stop. And from that stage, the object will continue falling with the same velocity and the same speed. So what that means is that once you reach that speed, it does not change. And this is what we call the terminal speed. So what we say is that when we achieve the terminal speed, which I am going to call v sub t, I'll use a capital T for it so as to distinguish it from time, then the derivative of the velocity will vanish. It will no longer change. So this gives us an equation for Vt. What we have is naught is equal to g minus c over m times Vt squared. So therefore Vt, our terminal speed, just bringing this over to this side and multiplying both sides by m and dividing both sides by c, and then we take the square root. So Vt is mg over c, all the square root. So that is the terminal speed. So what I want to do now is to rewrite our equation for the acceleration in terms of the acceleration due to gravity and the effect from air resistance, but I want to rewrite this in terms of the terminal speed and the speed as a function of time. So we have c over m here, and c over m is in this equation here. So from this equation, what we see is just taking these terms over to this side and dividing both sides by vt squared, is that c over m is g over vt squared. So therefore, dv dt, the acceleration of the object as it falls, is g minus, and now it's g over vt squared times v squared. And we can just tidy that up a little bit. G is a common factor, times 1 minus v squared over vt squared. And that is a differential equation that we want to solve on the next slide. So what we've done on this slide is we've modelled air resistance in this way. We've generated a differential equation, introduced this concept of terminal speed, the speed that the object is approaching for large times, and we've generated this equation. And let's now try to solve this equation on the next slide. So on the previous slide, we obtained this equation, and what I want to do on this slide is to integrate it and obtain v as a function of time. So what I'm going to do is divide both sides by this term in the brackets here, so that all the v dependence is on one side, and I'm also just going to swap the sides around. So I'm going to write that g is equal to 1 over 1 minus v squared over the terminal speed squared multiplied by the derivative of v with respect to t. And now we're going to integrate both sides. So we're going to have the integral of g with respect to t. G is of course just a constant, so that's very straightforward. Is going to be equal to the integral of 1 over 1 minus v squared over the terminal speed squared times dv dt integrated with respect to t. And this side here is exactly in the form of a substitution. We have a function depending on v of t multiplied by dv dt and integrated with respect to t, so we can write that down immediately as being equal to the integral of 1 over 1 minus v squared over vt squared integrated with respect to v. And at the end we will replace, v by v of t as a function of time. So this is what we want to integrate, and I would say the natural thing to do on this side of the equation is to multiply top and bottom by vt squared. So we get equals vt squared when we multiply the top, and on the bottom we have 1 over vt squared minus v squared integrated with respect to v. And on this side we have the integral of g with respect to t, and we can write that down immediately. So it is g times t plus some integration constant that we can fix later on. So to calculate the velocity as a function of time, what we've now got to do is to perform this integral. And when we look at this integral, what we see is that we have something which factorizes into vt minus v times vt plus v. So we're going to be able to perform this integral using partial fractions. So just to give myself a little bit of room, I'm going to squeeze together what we've written so far on this slide. So to perform the partial fractions, we don't really need to write out the integral. We're just going to look at the integrand. And what we have is that 1 over vt squared minus v is 1 over the product of vt, let's say plus v, times vt minus v. And this is a proper rational function because we have a polynomial in v on the bottom. Sorry, apologies, that should be v squared. Excuse me. So what we're going to get is a constant over vt plus v plus some constant, I'll call it b, over vt minus v. And if we add these together, combine them over our common denominator, so vt plus v times vt minus v, the numerator becomes a times terminal speed minus v plus b times the terminal speed plus v. Now, for this to be the same as this is a constant, so we need the numerator to be a constant and not to have any v dependence. And that tells us that the a times minus v and the b times v have to cancel. So we read off immediately that we need a is equal to b for the v's to cancel. What about the constants? We want the constant terms that are left here to be equal to 1. Remember, the denominators are, by construction, exactly the same. So the constants are a times vt plus b times vt, but a and b are the same, so the constants are going to be 2a times vt. So we also need that 2a vt is equal to 1. So therefore a is equal to b is equal to 1 over 2 vt. So we've performed a simple partial fraction expansion, and we know what a and b are. They are both plus 1 over 2 vt. So we can take this and substitute it back into our integral as the integrand, and now we're going to have two integrals which we can calculate. So let's just rewrite before we get ourselves confused. 1 over vt squared minus v squared is equal to, and it's 1 over 2 vt, that's a constant terminal speed, that's a common factor, so I'll pull it outside, times 1 over vt plus v plus 1 over vt minus v. And this is the way that I want to write our integrand so that we can perform the integral. So what we obtain is that gt plus c, that's what we have here, is equal to vt squared, and now I'm going to pull this constant that multiplies everything through the integral sign. So we're going to have vt squared divided by 2 vt, so we can see that one of the powers of vt squared will cancel with this, times the integral of 1 over vt plus v, and then we've got plus 1 over vt minus v, but that minus sign here is something which we might stumble on. So what I'm going to do is just rewrite it immediately as minus 1 over v minus vt. And this is all integrated with respect to v. So just to be careful, what I did here is I've just rewritten this by multiplying top and bottom by a minus sign. That's the minus sign for multiplying the top. And when I multiply the bottom by minus 1, I just replace the denominator by v minus v of t. So now these integrals are both going to be logarithms. So what we're going to obtain is, well, the vt over 2 is the simplified factor outside. That multiplies everything, so I'll open a big brackets. And then from the first term, we have the logarithm of the modulus of vt plus v, but I can also write that as, well, I'll write it as vt plus v. And then we have minus, and now this integral is also a logarithm, and it's the logarithm of v minus vt. Close the modulus, close the brackets. I could put plus an integration constant here, but we've got one on this side already, so I don't see any point in doing that. So now we've got the difference of two logarithms, and we know how to write that. We can just write that as the logarithm of the modulus of this divided by this argument. So what we obtain is g times t plus an integration constant is our terminal speed over 2 times the logarithm of the modulus of vt plus v over v minus vt, close the modulus. And this looks a little bit, apologies, this looks a little bit ugly. So it was vt plus v over v minus vt. This looks a little bit ugly because we've got vt plus v here and v minus vt here. Now v is going to start at 0 and it's going to approach the terminal speed. So v is going to be less than or equal to vt. So I think it's nicer to write that as vt minus v. And if you're worrying about the fact there's then a minus sign multiplying everything in here, it doesn't matter because this is a modulus. And the modulus of, say, minus 7 is the same as the modulus of 7. So what we can do immediately is we can rewrite this as gt plus c is the terminal speed over 2 times the logarithm of the modulus of vt plus v over vt minus v, close the modulus. And that is our equation. And what I want to do on the next slide is to work out what c is and also to rewrite this so that we have not t as a function of v, but v as a function of t. So we want to just rearrange this equation and solve for v in terms of t. And I'll do that on the next slide. So on the previous slide, we obtained this equation. And what I want to do first is to find the value of the integration constant. And to do that, I'm going to use the information that at time t is 0, we have v is 0, or v of t, if you wish to be a bit more explicit, is going to be 0. So it's being dropped from rest. So therefore we have, putting that into this equation here, that 0 plus c, because t is 0, is equal to whatever the terminal speed is. That just depends on constants m and c that we saw at the beginning, times the logarithm of the modulus of vt plus 0, because it's at rest, over vt minus 0. And this means that we have vt over 2 times the logarithm of 1, and we know that that vanishes. So 0 plus c vanishes. The solution is that our integration constant is equal to 0. So our equation is gt is equal to vt over 2 times the logarithm of the modulus of vt plus v over vt minus v, close modulus. And now what I want to do is to solve this and to obtain it in terms of v. And what I'm going to do is I'm just going to use an identity that I happen to know, and then having got the identity, I'm going to rewrite everything, but I will later on give you a proof of the identity on the final slide of this video. So, to use the identity, what I want to do first of all is in the argument of the logarithm to divide top and bottom by vt. And if I do that, we're going to obtain gt is equal to vt over 2, that just sits there outside, times the logarithm of the modulus of 1 plus v over vt divided by 1 minus v over vt. And the identity which we're going to use, and as I say, I'll prove it at the end, is that 1/2 times the logarithm of 1 plus x over 1 minus x is equal to the inverse hyperbolic tangent, so tanh to the minus 1 of x. And I will prove that at the end. So this tells us that we can rewrite this equation as gt is equal to vt, the terminal speed, the factor of 1/2 outside, the 1 over 2 here, is used in our identity, and that's times tanh to the minus 1 of v over vt. This ratio of speeds, the speed at time t divided by the terminal speed. So now we want to find v, and to do that, let's divide both sides by the terminal speed and swap the sides of the equations around again. And what we're going to get then is that tanh to the minus 1 of v over vt is equal to gt divided by the terminal speed. And now we take tanh of both sides, and tanh of tanh to the minus 1 is just going to be the argument. So what we're going to get is v over vt is tanh of the right-hand side of this equation, so gt over v. So we've just taken tanh of both sides. Tanh of tanh to the minus 1 of v over vt is v over vt, and the tanh of this side is that. Now, tanh is sine over cosh. So if you recall that tanh of x is sine of x over cosh of x, it is e to the x minus e to the minus x all over 2 divided by e to the x plus e to the minus x, also all over 2, and the factors of 1/2 top and bottom will cancel, so I'm not going to bother writing them. So that means that I can rewrite this in this way with x being gt over vt. So what we obtain is v, the speed, over the terminal speed is equal to e to the gt over vt minus e to the minus gt over vt, all divided by e to the gt over vt plus e to the minus gt over vt. And as we want v as a function of time, why don't we just say v of t is multiply both sides by vt, and then we have the terminal speed multiplied by this ratio of differences and sums of exponential functions. So this is our answer for what the speed will look like as a function of time. So we can ask ourselves a little bit more about this, whether this looks sensible, and I'm going to just do that very briefly on the next slide. So on the previous slide, we obtained the following two results for the speed as a function of time in terms here of the hyperbolic function, the tanh, and here explicitly in terms of exponentials. Remember, the hyperbolic functions are essentially just convenient combinations of exponential functions. So, what does this version here look like? Let's think about this one first. So let's just remember the graph of the tanh function. So it looks something like the following. So we'll say tanh of x, and it looks something like this, where for large x it approaches 1 and large negative x it approaches minus 1. So this is y is tanh of x. And if we look at the solution written here, for large t, we're going to get the tanh of a large argument that's going to approach 1. So this will approach 1 multiplied by the terminal speed. So we see that for large t, v of t is going to approach the terminal speed, which is exactly what we would expect. And at t is 0, we have v of t, vt, the terminal speed, multiplied by tanh of 0, and when t is 0, we have e to the 0 minus e to the 0, so that vanishes, so it is indeed dropping from rest. So at the time t is 0, we have 0 over 2, so this vanishes. So at t is 0, v of 0 is 0, so it's at rest. And that is really exactly what we would expect. If we look at it written in this way, we could perhaps rewrite the equation as v of t is the terminal speed that's setting our scale. And then what I'm going to do is divide both the numerator and the denominator by this exponential. So we're going to get 1 minus, and now we have 1 over the exponential already. If we're dividing it again, we're going to get 1 minus this exponential squared. And from the rules for powers, we just say this is minus 2gt over vt. And in the denominator, it's 1 plus e to the minus 2gt over vt. we start at t is naught. At t is naught, this exponential is e to the naught, which is 1, so it vanishes. So it starts at rest. And then as t increases, we are subtracting something smaller and smaller from this. And in the denominator, we are adding something which is also becoming smaller and smaller. So this is going to always be less than 1. And as t becomes very large, this is going to approach 1, and this is going to approach 1. So as t becomes very large, this approaches 1, which we know from the graph of the tanh function. So again, we see for large t, our velocity, or our speed rather, as a function of time, is approaching the terminal speed. And with that, I'm going to stop this discussion, except on the next slide, I'm going to give a proof of the relation between the logarithms and the inverse tanh function. So we'll see that on the next slide. So as promised, on the final slide, I want to show this identity. And it's worth bearing in mind that in our application, x is v, the speed at time t, divided by the terminal speed, which is the maximum value it approaches. So x is going to be between 0 and 1. So let's look at this and show that we obtain this from it. So let's say that 1/2 log modulus 1 plus x over 1 minus x is going to be something which I'll call y. We'll multiply both sides by 2, so therefore we have the logarithm of the modulus of 1 plus x over 1 minus x is 2y. And now it's very natural, I think, to take the exponential of both sides. So on this side, we're going to get e to the 2y. And on the left-hand side, the exponential of the logarithm of the modulus is going to be the modulus, and that's going to be 1 plus x over 1 minus x, because this is then going to be positive. Remember, x is positive, it's this ratio of the two speeds, and x is going to be at the most approaching 1, so this denominator is always going to be positive and the numerator will be positive. So this is what we get if we exponentiate both sides. So now we multiply both sides by 1 minus x. So let me just do that here. We have 1 plus x is 1 minus x times e to the 2y. And we want to find x in terms of y. So let's do that. So we have 1 plus x is e to the 2y minus x e to the 2y, just expanding the brackets here. I'm going to bring all the x terms over to the left and all the non-x dependent terms over to the right. So on the left-hand side, we are going to have x times 1, that's this term here. And then when we bring this term over to this side, it will become positive. We're adding it to both sides. So this is plus x e to the 2y. I've taken the x out already, so it's just e to the 2y. And on the other side, we have e to the 2y minus 1. So therefore, dividing both sides by this bracket here, we have x is equal to e to the 2y minus 1 over e to the 2y plus 1. I've just changed the order of writing these two terms so that it looks like this, which is a bit more elegant. And now, to see how this is related to the hyperbolic functions, let's on this side divide top and bottom by e to the y. So if we do that, we are going to get e to the 2y divided by e to the y is e to the y, minus, and 1 over e to the y is e to the minus y. And, we already see the numerator of the tanh function. And on the bottom, in exactly the same way, we're dividing the bottom by e to the y as well. We get e to the y when we divide this, plus 1 over e to the y, and 1 over e to the y is e to the minus y. So therefore, x is the tanh of y. So this tells us if x is the tanh of y, it means that y is tanh to the minus 1, the inverse function of x. So if this is true, we take the inverse tanh functions of both sides, and y is going to be equal to the inverse tanh function of x. Remember, y was our name for this, so therefore we have seen we've shown that 1/2 the logarithm of 1 plus x over 1 minus x, close the modulus, is equal to the inverse tanh function of x, which is what we wanted to show. And with that identity, I will stop this video.